Okay. Okay. I understand that some of the material you probably have encountered in your pre-university days. But the thing now, Chapter 3 will be moving to joint distributions, something that I believe, at least on the theoretical level, is not actually quite explained in the pre-university days. And then there are something more intricate. So I guess for those who are watching the webcast, you have to follow the material fairly well. And before we go on to something like Trebuchet Inequality, Trebuchet Inequality, Trebuchet is a very renowned Russian mathematician, a probabilist, as well as an analyst. Not only that, he has his school of mathematics. Very noted students include Markov and some other very well-known mathematicians. So we are going to talk about one such inequality. It is very often used in higher, in the more advanced probability modules, as well as in statistics. The basic advantage of the Trebuchet, I will repeat it when I'm coming to this, is that we require very minimum knowledge about the random variable. It's stated here that we only need to know the mean and the variance of the random variable, and that's about it. Now, of course, it would be too much to expect we are able to compute the probability here in an exact way, because to know the exact probability, you need to know either the probability mass function when the random variable is discrete, you have to know the entire table, or you have to know the probability density curve, which means you actually know the entire function, the functional expressions. Now, very often this is not available to us, so all we have is the variance and the mean of the random variable, and this is something that we are going to do in statistics. Towards the end of this module, will be if I want to know the mean and the variance, one way we can do so is to sample from the population, and then from the populations I have a good handle of the estimate of the mean and the variance. So what I'm trying to say is the mean and the variance are usually more accessible to us through a sampling technique. All right. So before we do that, let us recap one important concept is what we call the mean, or sometimes it's called the average. But we'll try to save the word average for samples, all right? Or the expected value or expectation. So we will use this of a random variable x. Okay, so we will use this terminology fairly interchangeably. Now, for discrete random variable, the expectation of x will be just a weighted average of the values of x. And the more precise formula is this. So you let f of xi, probability of x equal to xi. So this is the weight. Okay, and then you sum up all the xi. So the weighted average, to be more precise, is weighted according to the probability. All right, the probability that the value xi. So if the random variable take a particular value with a higher probability, you are going to give it a higher weight. So it has more influence on the average. The definition here is very much influenced by a frequency thinking. Something that we mentioned when we introduced probability, because this is when this is roughly equal to the number of times that the value xi is occur, and this is the frequency. And if you do it n times, repetitions, so this would be the relative frequency. And if you do the repetition a lot, then this number will be closer and closer to this. So this is the entire philosophy of frequency approach, meaning that the probability is actually is recovered by a long time repetitions of how often you get your value xi here. Now the continuous case is in the similar manner, x, and then this measures more or less the probability that the random variable is taking in this interval, small x, and then plus a dx here. All right? So this is measuring the probability here. And so the summation sign, to conform with the differential calculus, the summation sign will be changed to this, and we are running from minus infinity to infinity. So the definition, even though in terms of appearance they look different, but it is actually talking about the same thing. So again, this is the weight. All right? So, okay, so don't be fooled by the different appearance. They actually are very closely related. So one of the things is the center of gravity. You think of it as, so as a result, if this is your minimum value of your random variable, I'm talking about discrete case, and then this will be your x maximum. So meaning that the random variable will not take value outside this portion. So the expectation of x would be somewhere in the inside the minimum value of the random variable and the maximum value of the random variable. All right. Now, how about the variance? So so we also have this similar thing. All right. The lecture notes spend some time to explain this actually has two interpretations. One interpretation is that you think of it as a new random variable. And so if you're thinking of a discrete case, something that we have done, you have a table for x. But now, because of the transformation, you will open up a new row, and that would be taking the transformation g on each of the x that you have. And so, so you basically change your table, the x values to the y values, and then you do the weighted average. But anyway, I'm not going to spend time on this. So this would be, has two expressions depending on whether x is discrete or x is continuous. All right? So if it is discrete, then this is just, you still have this as before. But now you change this to, change your x to g of x. So that is the only change. And now here you also have this integral. But now this term is g of x. Okay, so this is it. And we have a special case The special case is g of x is equal to x minus mu square, where mu is the expectation of a random variable x. So here, this is measuring x minus mu is the deviation of x from mu, right? And we have seen that if we do not have a square, because mu is more or less the center, so you know that there are some x that would be less than mu, and some x would be bigger than mu, right? So as a result, if you are just simply adding these things up, you expect cancellations. And in fact, the cancellation is perfect. It is exactly equal to 0. So we need to get rid of the sign, all right? So one way to do so is the square deviation of this. So as a result, the variance of x is defined as this. So now we add in the word of the mean square deviations of the random variable x from its mean, all right? Now, another thing that is quite useful in terms of computation, you can have this. All right. Okay, so we have this. All right. And now what we want to introduce is the sections 6 in chapter 2, the Trebuchet inequality. Okay, probability and as well as statistics, part of the statistic I would say, the main concern is estimate the probability. I mean, I wanted to know probability. If I want to play with words, I mean, the main concern of probability is to compute probability, all right? But there are situations that we do not have everything. So if we have everything, then how do we compute this probability would be this. So this is saying that the random variable x, the absolute deviations from its center, x minus mu x, is not too far. I mean, it's within C of the C amount, all right? So this is what we are interested to compute. This is the central part of the random variable, so to speak, all right? For example, in confidence interval, we will try to choose a C so that it will give us a 95% probability. So that is where it comes from, all right? Okay, so this slide talk about the mathematician Trebuchet. I mean, he is one of the greatest Russian mathematicians. Probably another guy that you know is Kolmogorov. So Trebuchet is much earlier than Kolmogorov. The Russian mathematician Trebuchet gave a very useful upper bound or lower bound to such probability. This result is known as Trebuchet inequality. Now, this module is not concerned about the proof of this, but the proof is actually 1 or 2 lines. I mean, except that we have to introduce a little bit more notations, which I will refrain from doing it. In fact, I mean, I'm not boasting. I mean, any graduate student, if they are aware that this is going to be a very useful inequality, would have discovered it himself. But the fact that to be able to see that such an inequality is very useful is another thing, all right? Okay, so okay, this is the statement of Trebuchet inequality. So I'll just state the theorem first, and then I will explain, the meaning of some of this. So if a random variable x has mean mu, so the mu has to match with the mean of the random variable. So this is the mean of this. And then sigma is the standard deviations of the random variable that you know, you are interested. And I'm interested to find out what is the probability that x deviates from its center by an absolute multiple of the standard deviations. All right? Okay, so ignore about the statement of the inequality, but you have only two very minimal conditions or information, basically only the mean and the variance, and nothing more, all right? So, I mean, one of the examples we have seen in the last lecture is, if you still remember, we assign probability to -1, 0, and 1, with probability 1/4, 1/2, and 1/4, and then another random variable -1 and 1 with half and half. Both of them give you the mean equal to x, equal to 0. So what it says is that there are many, many random variables that give you the same mean and the same variance, all right? So the mean and the variance are by no means a unique characterization of the random variable. So you know very minimally about the random variable, just the first two, basically the first two moments, all right? And so the usefulness of this is that it bounds this. But let me give you reinterpret this number so that it is easier. And why this makes sense. Okay, so our concentration is this. So basically, we are looking at mu here, and then x is one of the possible values of this. And here, my main concern is that I wanted it to be quite far away from x. So one of this is this. This will be mu minus sigma, and mu plus sigma, and so on. So the interpretation of this is we divide the sigma over here. And so we are measuring the deviations of the random variable from its mean in terms of the unit of standard deviations. Now, to give you an example, which I think I know top of my head, in a lot of IQ tests, the population's mean is 100. Okay. So if you get your IQ test 100, then that means you are on the average. And then the standard deviation is 16. All right. Now, if I say if you take your IQ test and you happen to have 148, how do you understand how smart you are? Definitely, I can say you are smarter than the average because 148 is bigger than 100. But how do I quantify it? Now, one way to quantify is measure in terms of how many units of standard deviations you are above the average. So it is 148 minus 100. And the unit that you measure is 16, all right? Now, this is useful because whatever unit you are using, this is unitness. Is there such a word? I mean, all right? It does not have any measurement unit there. Now, if my context is in mean, but suppose the context is, say, the length or our height. So if this is my height, all right, 165 cm, and then I don't know the mean, so let's say in Singapore, maybe 170 cm. Now, I'm definitely shorter than the average. I know that. You don't need to tell me. But I mean, by how do I understand the 5 cm shorter? So the way you do it is you need to know the standard deviations. And suppose this is, say, the standard deviation is 10 cm. So in my case, it is minus half standard deviation below average. Now, this minus half makes sense because if we decide not to measure everything in cm, but let's measure everything in meter. And then this will be 0.1, right? Now, so I will be minus 0.05 unit lower than the average. But how do I understand this 0.05? Whereas here my measurement is 5. So we decide something that is independent of the unit of measurement. And so that is much better than it's much better to measure everything in terms of the standard deviations. Now this has a name there. I think for the Singapore students, you must have heard of the Z score and all this. In your PSLE, people talk about calculating your Z score and then later on change it to T score. I mean, the parents are especially interested and they think that it's very deep stuff that MOE is using. Nothing. I mean, basically, because in each test, say Chinese language test, I mean, it differs from year to year and differs from paper to paper. So what they do is they compute the average of the entire cohort taking the Chinese language paper. And so that would be the mean. And then they also calculate the standard deviation. And so they calculate, I mean, for each student's score, how much his score is bigger than the average and by what amount. The amount is measured in terms of the standard deviations. And then what they do is they move everything to 50. I mean, so that it is somewhere in the middle. So even though the average of the entire test may be like 60, they might move the whole thing to 50. So this is a standardization so that the PSLE score from year to year using more or less the same currency, so to speak. And then I think they change, as far as I know, I think you can get it from the MOE website. And then they change the standard deviation by a certain amount so that by scaling the thing, so that the standard deviation would be 10. So they basically move the entire empirical score to something like the average is 50, and then the standard deviation is there. And so they recalibrate the calculations in terms of this. So this is an advantage of measuring everything in terms of this. So this is what the Trebuchet inequality is trying to measure. Okay, most of the time the Trebuchet inequality is referring to this. I don't want to have very large deviations, all right? This part is actually, another thing is this is an upper bound. So this 1 over k squared is very conservative, all right? Okay, and so you can ignore this because once you, the probability here and this is actually the opposite of one another, all right? So that is why you have a 1 here and minus this probability. And since this is a lower bound, upper bound, and so you are subtracting something more, so this would become a lower bound here. Okay, so if you need to remember, you can just remember this one. So we are interested in the upper tail. Now, in a lot of science, we are interested in the upper tail, something that is extreme. For example, I mean, Singapore has been very dry, so we wanted to know the likelihood of extreme low rainfall within a certain month. Or for flooding, we are interested in what extent is the flood will exceed a certain level. In Olympic Games, you are interested in the smallest the shortest time in a race, or in a lot of high jump or other thing, you want the longest thing. So we are interested in extreme. We are not too interested in the middle portion. Okay, but this is actually a conclusion from here. Okay, so this is measuring in terms of k unit of the standard deviations above the average. All right, so this is the absolute deviations is k units, at least k units of the standard deviations. All right, so this is, you put it in word. And so the probability is just 1 over k squared. It has nothing to do with sigma. It has nothing to do with mu, because if I move the sigma over this side, this is our set score. So we are basically measuring something that is not unit, something that has no unit in it, and so and it has nothing to do with the random variable anymore. So the fact that you need to know the random variable about the mean and the standard deviation is in this interval here. All right. Now this is one way you can remember, but this is the way I usually remember because the way it is, I have to rephrase this portion in terms of unit of sigma. But this is another way of remembering the thing. So suppose I wanted to, I have no choice, okay? It's still the deviations, absolute deviations from, all right? And I'm interested in t. So that would be the variance of x over t squared. So this would be one way to remember the Trebuchet inequality. Now this is the same form because if t is equal to k sigma, then so this would be sigma square over k square sigma square. So this is 1 over k squared. So this is just another form of formulating the Trebuchet inequality. So it is a matter of your personal preference, whether you wanted to remember in this way, then you don't even need to convert everything in terms of multiple of sigma. But then, of course, you have the sigma will appear here. All right. But I think if you are remembering this, it would be easier to do your tutorial in the form that I wrote. But it's not much, shorter. Okay. Yeah, sorry, I keep going back and forth. So now I wanted to deduce this. Okay. And this would be equal to 1 minus all right. And since I have I might have an overestimate in this, so that means if I subtract this, I might subtract something bigger. If I subtract something bigger, my number will become smaller. All right. So I will have this. Now another thing is here. This is how we formulate this in our slide. But it really doesn't really matter whether you have an equal sign here, and if you have an equal sign, then you will have a strict inequality here, because basically we have very little knowledge about the random variable. All we know is about its mean, its center, and then how the spread is. So we will not be able to be so so precise about estimating the probability. All right. So we will not be able to track whether it is equal or strictly bigger than. All right. So something that unless we know much more about the random variable, then we will be able to do so. So the beauty of this Trebuchet inequality is generality. Okay, and we will have examples that this estimate is actually can be very crude, meaning that the probability you are trying to get is maybe much smaller than the upper bound. But there are also examples saying that you cannot improve this Trebuchet inequality. Now these are something very fine, and probably I don't want to bother you. This inequality cannot be improved further, meaning that you cannot have a smaller constant times 1 over k squared. All right, 1 is the only is the choice here. So there are examples that the two sides are almost the same. All right, so you can't really improve this further without assuming more about the random variable. Now when k equal to 2, so we substitute k equal to 2 into here. we conclude that the bold phase is important regardless of the random variable. As long as the random variable has a mean and has a standard deviation, then the probability that it would be at most 1/4 chance that it is 2 standard deviations or further away from its mean. All right? Now, using the example that I just mentioned, your IQ score is 148, and that the average is 100, and then the standard deviation is 16. So your IQ is 3 standard deviation above the average. And so your probability at most is something like 1/9, right? But we are talking about two-tailed. Let's say if it's symmetric, then the probability can't be bigger than 1/18. So 1/18, you take it as 1/20 is about 5. So you are definitely on the top 5% percentile. I mean, this is a very conservative estimate. You may be actually much better than 5% at the top. You might be even higher up in the percentage. But without knowing the IQ curve of the general populations, I can say something about how smart you are. You are definitely within the top 5%, all right? So if you score 148. And in fact, if you know what is normal distribution, people observe that the IQ score actually follow very closely of a bell curve. And so now if you're 3 standard deviation above the average, you are actually within the top 0.5% of the cohort, all right? So you can see the estimation can be quite crude here. But anyway, we are able to say something about this. The beauty is this is true for any random variable. It's not just for one particular random variable or a class of random variable. So for most distribution, it is unlikely for a random variable to be more than 2 standard deviations from its mean. Well, I think this statement is a bit kind of vague. It's a relative statement. Unlikely here, it is saying that it's something like 25%, all right? So, but if you think that 25% is likely, is all right, then this statement may not be correct here. So whether something is likely, I think I mentioned it. If your surgeon tell you you have a 5% risk of the operations, you will still go for the operation because 5% is kind of small. But if you, this ceiling might collapse with 5%, then this is definitely not acceptable, right? Okay, so what I meant is 5% can be reasonable or 5% can be very unreasonable, depending on the kind of problem. Okay, so the subsequent of the examples are basically illustrating this. We are either estimating the deviations above or within the deviations, all right? And we usually give you the mean and the standard deviation. And then so things are actually quite mechanical here, the example. It is because the beauty of the Trebuchet inequality is in its generality, or it's not in specific example. Suppose that it is known that the number of items produced in a factory during a week is a random variable with mean 50 and variance 25. So we have to convert it into standard deviations. So what can we say about the probability that which production is between 40 and 50? Now, the mean is 50, so that means it's 10 below the average and 10 above the average. But the way I understand the 10 now has to be measured in terms of the standard deviation. The standard deviation is 25. The variance is 25, so the standard deviation is 5. So basically, the statement is now what is the which production is within 2 standard deviations from its average. Okay, so this is the way we convert this, and so we have this. Now, in this lecture notes, we added in an equal sign. You might want to delete it, but it's not going to affect your answer. Because mathematically, this sign is a little bit bigger because it includes the endpoint. So to make sure it is an equal sign, I would take away the equal sign here. So it would be strictly less than. Now this is something within, it's not deviating very much. It's about the center. So the Trebuchet inequality would be a lower bound here, and it would be 1 minus this. So what it says is that 75%, which is a very conservative estimate, at least 75% of the week, your production will be within 2 standard deviations from the mean. So this is a good guarantee, at least. I mean, if 75%, if you are producing something not very, you don't need to be very precise. I mean, as opposed to precision measurement. Suppose you are talking about, I mean, the weight of a loaf of bread and all this. So I think you won't really mind whether it is, I mean, differ in a certain amount. Okay, so the daily production of electric motors at a certain factory average 120. So we give you the mean and also give you the standard deviation 10. So use the Trebuchet inequality to find an interval that contains at least 90% of the daily production level. Now here we are doing it something very conservative, all right? So, so basically the question is asking this. So X is measuring the number of electric motors that are being produced. And so we are measuring 120. And so we wanted to at least, okay, we wanted to find this number so that this is at least 90%, all right? So 0.9. So this is the what the question is asking. So the way to solve it is we go about this. Okay, let me peek at the slide first. Okay, and we are thinking of K sigma. So sigma is given. So we know this. We know, of course, we know this. So this is the thing that we're interested. And this is by Trebuchet inequality. It's 1 minus 1 over K squared. So here what we do is we link up this inequality because this is what we are interested. So if we impose this is bigger than 0.9, then I will have this chain of inequality, right? So the Trebuchet inequality is giving me the intermediate. But you will know that your estimation is going to be very conservative because you actually go through 2 inequalities here. And Trebuchet inequality, as I mentioned, can be very conservative. But what it says is that, okay, let me solve the K first. So 1 minus K squared, I would take it equal to 0.9. And so as a result, K squared is equal to 10. And so K would be somewhat like square root 10, right? Okay. Now, let me say it again. The estimation here is conservative, meaning that you can guarantee 90% chance that it stay within this much. All right. In fact, in some situations, you might be doing much better. You might be actually achieving 99%. But So this is still at least 90%, all right? So, so this is how the slides go. So I'm just thinking of the deviations within k unit of standard deviation plus or minus. So this is by Trebuchet inequality. And so I impose that this is the lower bound here. That would be at least 90%, this quantity. So after I solve this, k is equal to square root 10. So I will have this number. So the interval we seek would be between 88.4 to 151.6. And we guarantee this interval will achieve a probability at least 90%. But it could be much better, all right? So a note on Trebuchet inequality. As the Trebuchet inequality is valid for all types of random variable, we cannot expect the bound on the probability to be very close to the actual probability in most cases. So the estimation can be quite rough, but we know there are cases that the estimations is also very tight. I mean, so you cannot improve it much. All right, so I guess we will have a break here. So can you come back at, say, 10:50? We'll be, I think in terms of material, the joint distribution probably, in terms of two levels. One is the understanding, because we are now trying to understand as a multivariate thing, which from your calculus, you know a multivariate calculus is usually more difficult than one variable calculus. And then another thing is technically it is also difficult sometimes, because it now may involve integration with on a 2-dimension or 3 dimensions or whatever dimension it is. But we will stay put with 2 dimension or 3 dimension in this module. Okay, so so we have a break here. Okay, I have an announcement to make. It's about the what topic will be covered in the midterm test. The midterm test will cover all the way, including 3.2. So we'll be covering until the end of sections 2 of chapter 3. All right. So I think there are other questions. Maybe I'll try to answer it, because in email it is not very efficient way of doing it. The first thing is about clash of midterm test. I think there is clash as of holding the test at the same time. This I think it doesn't happen, because our class is very huge. We occupy most of the space of the hall. So the clash would be understood as either you have a back-to-back test. So this is, I did not make it very explicit in the Word file. So if you have 2 back-to-back tests, we'll try to arrange. So suppose you have a test before my test, then we allow you to take the test, say, 15 minutes later. I'm assuming that your earlier test is held in within the multipurpose hall. It's not held in, say, School of Computing or Business School. That is the basic assumption. If my assumption is not correct, then let me know. Then I will allow you a bit more time to come to the test venue. So basically now I allow you, if you have a test just immediately before my test, I allow you to take it 15 minutes later. But if you have a test immediately after my test, then we will make provisions for you to take the test 15 minutes earlier, so that you can leave 15 minutes earlier for your next test. Now, there are such one case which may not happen, I think. As of now, some student has 3 tests, and they are all back-to-back. So one is 9 to 10, and then mine is 10 to 11, and then he has another one, 11 to 1. Maybe we can use Trebuchet Inequality to estimate this probability if we know enough. So for if you take 3 tests back-to-back, I think there is no NUS policies for midterm tests, how many midterm tests you can take in one day. I mean, the unlikely scenario, say if you take 5 modules and they are all held on the same day, tough luck, all right? But I think we'll try to adhere, make some change. We'll try to adhere to the exam policy of NUS, meaning that you are not supposed to take more than 2 examinations within 24 hours. So for students with 3 tests, including mine, that you have to do it on the October the 5th, Saturday, let us know. We will let you have a choice whether you want to go through the hardship of having 3 tests in one day. You clear it, so at least you can enjoy your movie later on. Or another option is you will be given to take makeup test. All right, so that would be your choice. But whatever it is, if you need to request to take your test early because you have a test coming immediately after mine, or you have to take my test a bit later because you have a test immediately before mine, let me know. And if you have 3 tests, unfortunately, we give you an option to choose whether you want to have a makeup test. Okay, and then your makeup test will be your midterm test. Okay, another thing is about calculator. I mean, these are the kind of calculations you are going to encounter. We allow you to bring in any calculator, programmable, graphic calculator, or whatever. But of course, we won't allow you to use your handphone. I mean, the only thing that we don't want you to do is to Google or do some search, all right? So if one day we allow you, then we'll make the questions that is not searchable. So, I mean, so it's your choice, all right? My advice is don't spend the money if you don't have a very fancy calculator. I mean, save your money for buying your data so you can do other things, watch video or whatever. Anyway, you have better use of your money. So don't spend the money just for the fact that we allow you using any calculator. And then there is another question that a bunch of questions that I don't quite anticipate. I think probably it is a carryover from A-level or your IB stuff. The question is, how many decimal places of your answer should I give? I guess I don't have a very black and white kind of answer. So I would say exercise your judgment. Now, of course, coming from me, calling your judgment is unfair because the judgment is with reference to my judgment. So if my judgment and your judgment differ, so you might think that you will suffer. Okay, I think we are reasonable people. I mean, for us, the ultimate aim is, unlike in A-level exams and other public exams, is to maintain a very strict standard of fairness, all right? And here, I think, at least for the university education, we care more about whether you understand things. So if we feel that you understand it, and if you give me a 3 decimal place, and then my answer is 4, or your answer is 4 and my answer is 3, I won't fault you about that, all right? And then another thing is whether you should give a fraction or give a decimal, decimal representation of the number. Again, we don't split hair, so we don't dwell on something very minor issue. The more important thing is whether you understand what's going on. So whether you give me 1/9, or 0.11, it doesn't really matter. And then how much you have to explain in your calculations. We actually haven't figured out our session B yet, but your questions preempt this. But probably your question is more relevant to final exam, how much I have to explain. Again, it is a matter of judgment. It depends on whom you are explaining it to. So a rule of thumb that would be useful for your presentation for other modules is assume your audience is as smart as you are and as informed as you are, except that he has not studied this particular topic. So meaning that you have to fill in the detail how you understand it. And so that would be the detail that you want to. You don't want to start from A, B, C, or 1, 2, 3. That would be, you will be underestimate your audience intelligence, or you overestimate your the intelligence of the other guy. Oh, you all know this, no need to present. Then that's it. I mean, so there is an extreme. You explain everything as it's to an idiot. Oh, I'm being recorded, so I'm in trouble. Or you want to explain to someone, like Einstein. You don't even need to explain to him. Then, so you are somewhere here. So you explain to someone like your university peer, your peer around your level. Then if you think that the way you explain to your peer about your same intellect, and he would be able to understand, so that would be the level you want to pitch, all right? And I think the concern is about the integration, how much detail you have to show. Of course, I think we won't dwell into the mechanic. Probably the most important detail I'm looking for is you give me the integrand in a correct way, and then you give me the limits of the interval of the integration, correct? Then how you integrate it would be something minor. And then if you screw up a little some detail for your final answer, I think that will probably overlook it unless you are looking for the variance. And then your variance is, after a lot of calculations, then you get a -3. And then you submit it. Or at least you cross it out, say that, oh, something wrong, right? I mean, you admit it. But you say -3 is the correct answer. Then it is a cardinal sin, all right? So it's not pardonable. So, okay, but we'll make a call. I think the main emphasis is understanding. I feel that you understand it, what you're writing. So let me do the judgment call, all right? Okay, so we wanted to talk about joint distributions. I think in your calculus, or whatever you learn in your high school, you always learn with only one variable. But you know the world is much more complex than one variable at a time. So here we need many variables. Here are some example. Okay, so section 1 is actually very simple. Now, very often we are interested in 2 or more random variables at the same time. For example, in the population of NUS students, our record, okay, it is actually much more complex than this. But if you imagine it is like a spreadsheet or Excel table, each row is a student. And then I will have the student's age or the year of birth, and then the year when he starts to join NUS, and then his or her gender, and then what is the major. And in fact, there are many, many other things. But of course, for this kind of thing, you guys are from computer science. People don't save it in this way. They save it as a list, and then the elements of a list is again another list. So probably it would be saved in this form. And it has the advantage of saving this in this form is because it can grant us different people to access the student database to a certain level. Suppose I can only access what are the modules you are taking. I would not be able to know where you stay and what your parents' name and all this. So certain different kind of people will be allowed different kind of access to how deep your list can go down. But here, without further complications, here for simplicity, every student in NUS will have these 4 variables to describe it. So if you're thinking of an Excel table, there are only 4 columns. Okay, there are basically 5 columns, so to speak. For example, the first column is the name of the student, and then the second column is his age, and then the third column is the gender, and then the fourth would be the major, and then Y is the how many years the student has been with NUS, and so on and so forth. So you basically have a table here. Now for each row, now I will have 4 variables to describe a subject in the populations. Okay, this is another example. For any particular day, we are interested in the number of vehicle accidents, how many deaths in these accidents, and how many major injuries on the road. So suppose I take a particular road, the junction where the Clementi Road and the Cambridge Road, the intersection there. We are interested in counting a number of features, number of accidents, and then as each accident, how many vehicles are involved, how many deaths or how many major injuries happen for that particular thing. So we tabulate this kind of things. Okay, now there is a slight change of the word. In the previous chapter, we call it random variable because we are thinking of one variable at a time, but now we have a random vectors. Random vectors refers to a vector each of the component is random. All right. For example, random as of number of vehicle accidents, and then D is the number of deaths, so it might vary from day to day, and then number of major injuries, I, is also random. So basically, a random vector is consisting of random variables packed together, okay, referring to the same outcome. Okay, here it's like this. Let E be an experiment, and then as a sample space associated with this, we are going to draw a diagram similar to the random variable soon. Let x and y be two functions, each assigning a real random number to the same outcome. So we call xy a two-dimensional random vector or two-dimensional random variable. All right. So in a way, we try to reserve random variable referring to one dimension. So we'll try to stick with random vector. But sometimes we do switch back to random variable because a lot of articles or literatures or books, unless it is very mathematically inclined, then people will just simply call it random variable, even though it is a vector. So the range space is now, if it's two-dimension, the range space is two-dimension, all right? So because it captures the values that x can take, and then the other variable, the other dimension is the values that the other random variable y that can take. So we have this. The above definition can be extended to more than two random variables. In fact, the two examples we have seen, the first example about NUS students, it would be I pick a student and then I will have four values associated with the student, the age, the gender, and the year, and also the major. So I will have four numbers for one. So what I'm thinking of is the vector is actually in a four-dimensional space there. The second example is about the accidents and how many deaths, and then how many major injuries. So I will have three variables. So again, now I'm living in three dimensions. So the range space would be three dimensions because each of the numbers of the vector corresponds to the corresponding random variable there. Okay, maybe I do. So this is the definition here. All right. Before we do that, let me draw you a picture. I'm not sure whether it helps or it might make it worse. All right. But this is sort of relate to something that we talk about random variable. So we have, again, this is where the experiment is. So the randomness is coming from here, but I have two, this is a two-dimensional random vector. And we call it x and y. So basically, you can think of, I have two rules of assigning something. And now, it would be assigned in my range space will be small x and small y. And if I have a s here, so under the x, it would be mapped to the x coordinate of here. And then under the y, it would be mapped to a small y. So that is where this thing is. As contrast to our one random variable, because we are just looking at here. Okay, so here I will just have a two-dimension. So again, purely our extension of our imagination. If you have a three-dimensional random vector, then you will be mapping into x, y, z here. And if it is higher dimension, of course I can't draw it, but I can still keep it as a list of number or a vector. Okay. So this is n-dimensional. Nowadays, this is, n is actually very, very large. For example, suppose you are keeping track of people's financial portfolio. The investor might have invested many, many stocks. So, X1 is the stock price of his stock that he invested. X2 will be the second stock, and so on. So, you have a very large N here. Or if you are keeping track of, say, the Singapore Stock Exchange Index, it might be a basket of a lot of stocks. So again, the N can be large here. So you are keeping track of all this. Or now weather. X1 might be the temperature, maybe in the morning, and then X2 might be the temperature at night, and X3 is the wind, and also blah, blah, blah. So you are keeping track of a lot of variables. Now this is going to be the trend, something people call big data, or whatever word they use. It's basically nowadays with the availability of computer memory. The computer memory is getting cheaper and cheaper, and also internet make it capable of depositing the information in one central place. So this is very big. Now, one such example I came across is, say, some supermarket actually keep track of people's buying pattern, especially you use your membership card. Okay, so they give you something, but at the same time, they know your entire track. So X1 might be whatever item you buy. X2 is the second kind of item. So they know actually, they also know when you go, most of the time, and how much you spend. And then what are the things, when you buy this, you will buy this. So from the supermarket point of view, if they know a lot of people buy one thing, and then they would buy the other thing, they would have a sale for one thing, and then you will buy the other thing, even if it's not on sale, because you make a trip there. Now, there are other people actually keeping track of other things, credit card. Sometimes they track more than one people, and then they found that these two guys, even though they are charging their own credit card, but they are all almost the same place very often. If it's a male and a female, you suspect something is going on. Overseas, and then when they are here, they all charge their own credit card. But if you are putting two random person, if you are tracking more than one people. Now, I'm not sure whether bank is allowed to do this, all right? Because they actually have the informations. So they might be able to track which group of individuals they are almost always spending the money around the same place, around the same time. Then you know they are always together, all right? How do you make use of all this information is another thing, but you might be able to track certain situations. So X and Y, now we restrict ourselves to 2 dimensions. So it can be very scary. But if you are just like an ordinary person like me, I have nothing to be scared of. Now, if you go out and you might be captured by the CCTV, right? Yeah. We had some incidents. One of our students in our computer lab steal the mouse of the computer. Then he thinks that it's fine. But actually the computer lab has a CCTV, so we know could accidentally take away the mouse of the computer. So okay, so we contacted him. Oh, hello. You have accidentally taken our mouse. All right. So a lot of informations, yeah, is available. So now X and Y is 2-dimensional discrete random variable. Now we only study 2 classes, but you can imagine there are many other classes. Now, a random variable is classified as discrete or continuous. But now I have a list of random variables. So presumably, I can have some of the random variables in my vector to be discrete and some of them to be continuous. But for the simplicity of this module, the components are either all discrete or all continuous. So we will be dealing with integration or differentiation on one side, and then summation and subtraction on the other side. We won't have a mix in that sense. Okay, now if you use a 2-dimensional discrete random variable, now again we can tabulate. But this is what we call cross tabulations. All right, we will show it soon. Okay, x and y is a 2-dimensional continuous random variable if the possible values of x, y can assume all values in the same regions of a Euclidean plane R2. So presumably if you are looking for definition 5, a 2 random variable, x can be discrete, y can be continuous, but we won't deal with these situations in this module. So example 5, I think it is belong to definition 3, a 2-dimensional discrete random variable. Okay, consider a television set to be surface. So the sample space S is one of a particular television set that is being sent to the surface center. So now I have 2 numbers to track this particular television set. So x is the age of this television set, which is rounded to the nearest year, and y is the number of defective components taken to the surface center. So let x and y. So x and y is a discrete 2-dimensional random variable, and the set of possible values will be so and so here, where n is the total number of components in the television. Okay, it can't exceed, right? I mean, more than the components. So an example, x, y equal to 5, 3 means the television set is into the 5th year, and then the number of components that are defective is now 3. Okay, fast food restaurant. A fast food restaurant operates a drive-up facility and a walk-up window. On a randomly selected day, x is the proportion of time that the drive-up facility is in use. At least one of the customers is being served, or someone is in the queue. And y is the proportion of time that the walk-up window is in use. So we are interested in having this 2-dimensional random variable. Now each random variable in itself is a very well-studied subject. It's called a queue. Queuing theory basically is about services and people waiting to be queued. You guys are from computing. The counter can be as a server, and then the customers are actually the jobs that you are submitting to the server to be executed. So the computer actually exercise some queuing discipline, how to handle it. Now, one of the things people are interested to analyze is, do we have a very long queue? All right? And now, if that is the case, for customer service, I might want to have more counters. But on the other hand, if the counter is idling, that is why they are looking at the proportion of time that the facility is in use. So the complement would be the proportion of time that the facility is idling. Then from the employer point of view, if the idling portion is is too much, then that means the productivity is low, so I might want to do something about it. All right. So now the joint distributions, as in 1-dimensional random variable, we would like to have a number associated to the probability or the probability density of a 2-dimensional random variable to take on a certain value. Okay, this is what we call a joint probability mass function. Let me have Okay, so this is the definition. So this is an and statement here. So so let me I don't know whether it's expanded. Okay, so it didn't quite expand. This is a shorthand notation. This is a shorthand notation. Okay, what it actually means is all those outcomes in your sample space so that x of s, y of s is equal to xy. All right. So this is the properly long version of because the probability calculation is inherited in the sample space because that is where the randomness is occurring. Now, I think this is, but I wanted to explain this a little bit more. All right. So the probability of x equal to x, y equal to y, in a way, it is actually equal to this event intersect this event. All right, so we put a comma here. Basically, we have two statements, meaning that both statements have to be true at the same time. All right. So both statements need to hold. So this notation generalized to higher than 2 dimensions. If you have blah 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 blah, then all the statement has to be true at the same time. All right. So okay. So this is it. Now, so this would be a function of small x and small y. The values that the random variables x takes and the value that the random variable y takes. And so we collect them, and this will be a function in small x, small y. But because of the fact that under this definition, the thing that we are looking at is a discrete random variable, so we only have a finite number of possible x and a finite number of possible y. So the tendency for us is to make a table out of this. All right. So before that, we have these situations. So this is coming from the probability because of here. All right. So this is non-negative. All right. And then this is always less than or equal to 1 because the probability can't exceed 1. So so we have this. And then the sum here means you sum up all the possible probabilities that the x can take, and then the random variable y that can take. So you add, you basically sweep over all possible possibility. Then it is equal to 1. Okay. And now here, this is let A be any set consisting of pairs of xy values. So A is a subset of a 2-dimension, all right, of a 2-dimensional plane. Then the probability that x and y as a random vector is taking values inside A is defined by summing up all those small x and y, the point that is in A. So here, this is another way to represent it. So suppose this is your A. So you pick x, y here. So the probability that x and y taking values in A. So you imagine you still have the sample space here and map here. All right. So what you do is you add them up. Now, very often this is a double sum, but it's just meaning that you are adding up whatever it is. So here you just basically add up whatever values in A that is defined there. Okay. So Okay, so find the value of k so that the function given by this can serve as a joint probability mass function. This example is trying to illustrate this property, all right? The property that of 1 and 2 here, all right? So you have an unknown. This is very similar to your tutorial this week or next week. You have an unknown, but you also have the fact that the total probability has to be 1. So you will have an equation there, all right? So the k here, we can pin it down because we have the information. Okay, so so in a way we have this. Maybe a better way that I would prefer to do it will be this. So fxy, xy equal to k times xy, x and y equal to 1, 2, 3, right? Okay, so one way you can think of it is this is x, this is y. So you tabulate this. So this is 1, this is 2, this is 3, this is 1. Okay, so this value is when x, small x equal to 1, small y equal to 1, so it's equal to k. So this is equal to 2k, this is equal to 3k, this is 2k, this is 4k, 6k, 3k, this is 6k, this is 9k. But then you know the sum of all of this is equal to 1, all right? And so, k is, so there are altogether 36k here, and it has to be 1. So k is equal to 1 over 36. Now this is just a table form, but of course if you really want to plot it as a function, which is a bit not so easy. So you have a x and y, so you think of it as 1, 2, 3, and then you have a 1, 2, and 3. So over here, over here, over here, and then over here, over here. All right, so you have these 9 dots. This represents the locations. And then, so here it would be of length k. And then at 1, 2, the length is 2k. And then here the length is 3k. And so on and so forth. So you can do it for the other 6 points. So of course, it does not help much, I mean, by thinking of this. But this kind of thinking is very useful for probability density function. But because we actually replace it in a table form, we flatten it, and then for the entries here, we replace it by k and so on. So this is just how the function looks like. The function is actually coming from R2 to R. So you have a 2-dimensional function, 2-variable function. So to plot it, it has to be 3-dimensional because you have to allow 1 dimension for the value of the function. So you will see gradually it would exceed our kind of visualization. Suppose you have 3 variables, x, y, z, then plus the value of the function, you are living in a 4-dimension thing. So some people is capable of imagining 4 dimensions, but I don't think they are capable of imagining, say, 100 random variable, 100 dimension. All right. So the way they usually think is they basically cut it in pieces, just like our how we step the real solid image. We basically look at each plane, and then we pack up the plane, and then so we reconstruct back the 3-dimensional image. This is how the scan actually works. I mean, they actually scan, each of the plane and then stack them up. All right. So, but this is a bit more useful, I suppose. All right. Okay. I think we will try to finish this example let me see first. Okay. So we'll try to finish this example, and then we will pick up where we leave off from today. So a company has 2 production lines, A and B, which produces at most 5 and 3 machines respectively. Assume that the number of machines produced is a random variable for each x and y, and somehow they are related. So let x and y represent a 2-dimensional random variable yielding the numbers. So this is the actual information. All right. So what is the probability that? So I have printed out this thing because to answer the first question here. Okay. So what is the probability that more chips are produced by line A than by line B? So this is one of them, because here line A, so actually I would prefer this is A, this is B, and then this is big A, big B. But of course, I mean, we will be using the symbol for different things. So of course, I think this is why the slides is produced in this way. And this is the case when A is equal to 2, B equal to 0. So you are basically adding up all this. So this is more or less the diagonal. And you don't want the diagonal. And you only add this thing up. So that is how the numerical examples is doing. So you basically add up the right things in the table. All right? Is that all right? Basically, this is a statement. So when will this statement occur is to sum up all those x equal to small x, y equal to small y, summation, as long as small x is bigger than small y. So this is actually the meaning here. The probability of x, y belongs to A. So we are using the same definition, except that I'm just spelling this out. And so we have to go back to the table and then see what are the places to add and what are the numbers we need to add. So this is it. Okay, so I hope it should add up to 0.73. All right, so maybe I'll stop here.